Good afternoon, everyone, and thank you for coming. Today, we have the pleasure of having with us Eduard Vilalta, who's a postdoc here at UAB, and he's going to talk about C-star algebras and the Elliott classification problem. Thank you very much.
Okay, so thank you very much. For those of you watching in YouTube, I had a very nice joke, which I'm not going to repeat. And yeah, as you said, I'm going to be talking about C-star algebras and the Elliott classification problem. Now, this talk is going to be slightly different than the ones that I usually give, because I'm not going to be talking about my own research, and instead I will be discussing one of the cornerstones in the theory of C-star algebras, which in some sense is the culmination of the Elliott classification problem. Now, this theorem that I will be discussing is an extremely deep theorem which took more than 40 years to prove. And it's not just the product of a single person, but it's the collaborative effort of many, many people. So in particular, it has a very rich history behind it. So even if some parts of the talk get slightly technical, I hope that you can still follow the history of this result and see how a very ambitious program was approached. And so a very quick disclaimer, precisely because it has a very rich history behind it, and I only have 30 to 40 minutes to talk about it, I will be missing some results and the name of some people who I otherwise wouldn't be missing. So yeah, if you're interested in this stuff, just talk to me afterwards and I'll give you some references where all the names that should be here, are in those references. Okay, so without further ado, okay, does this work now? Yeah. Okay, so without further ado, this is the theorem that I'm going to be talking about. So it's a theorem by many hands, and it reads as follows. So separable, simple, unital, nuclear, Z-stable, C-star algebras satisfying the UCT are classified by the Elliott invariant. Now, obviously, I don't expect any of you to understand any of these words. But the point of the talk is for me to define what these words are, at least informally, and to sort of justify why this result is deep and also meaningful. And so, as you can see, the theorem is about classifying certain objects with certain assumptions using some invariant. So the first thing that I'm going to do is to explain what these objects are. So I'm going to define what system object is. So in order to do that, let's take an algebra over C with some norm and some involution star, such that the algebra is complete with respect to C. So Cauchy sequences exist with respect to this. They have a unique root. So given such an algebra, one says that A is a C-star algebra if this inequality and this equality are satisfied. So mainly, you want the norm of A times B to be bounded by the norm of A times the norm of B, and the norm of A squared to be the norm of A times A star, where this equality here is known as the C-star equality. So this is what a C-star algebra is. I'm going to give examples in a couple of seconds. But before doing that, whenever you define an object, in this case C-star algebras, something that's always useful to do is to define maps between these objects. And so given any pair of C-star algebras, I will say that an algebra homomorphism between them is a star homomorphism if it preserves the involution star. And a non-trivial but easy consequence of the C-star equality is that such maps, so star homomorphisms, are non-continuous. So that's why we do not ask it in the definition. This is something that you need. So these are C-star algebras, the objects that we want to classify, and the maps are called star homomorphisms. So the first example of a C-star algebra is the simplest non-trivial C-star algebra there is, which is the complex numbers. So the complex numbers is a C-star algebra when you equip it with the usual norm and the involution given by conjugation. Now, to be more explicit, C is obviously an algebra over C. It's complete with respect to the usual norm, as we all know. And you can just directly check that the C-star equality is satisfied when you set involution to bits. So C is a system. More generally, if you know what bounded and compact operators are, you can show that the algebra of bounded operators over any vector space is a C-star algebra with the usual norm and involution. And the same thing can be said about compact operators. So it's not just C, it's bounded operators, compact operators. And these examples I'm not going to use in this talk, but the one that I will be using throughout is this. So mainly, if you take a locally compact Hausdorff space, you can consider the algebra of continuous functions from X to C that vanish at infinity. Okay, for a compact space, this is just all continuous functions from X to C. And this is an algebra with pointwise addition and pointwise product. And you can make it into a sister algebra by considering the supremum norm and the involution given by pointwise conjugation. Okay. And again, you can just check directly that the sister equality is satisfied and that inequality is also satisfied. So these are all examples of sister algebras. In particular, for any locally compact Hausdorff space, we get one such example, so C0 of X. And we don't get just any sister algebra, we actually get a sister algebra that's commutative, meaning that the product is commutative, because the product is the pointwise product. In fact, one can show, and this is the first sort of deep statement that I'm going to state, that all commutative sister algebras are of this form. So if you take the definition of a sister algebra, and you assume that the product is commutative, then you can find a locally compact Hausdorff space such that C0 of X is isomorphic to A. So in this, or partly because of this, okay. I don't know. Okay, well, so partly because of this result, one often sees the study of sister algebras being referred to as non-commutative topology. The idea behind this is that for commutative sister algebras, when we are studying commutative sister algebras, all we are truly doing is studying topology, right? Because of this. So in the non-commutative setting, you can say that, well, in the non-commutative setting or the general setting, we're studying non-commutative topological spaces. So it's just a useful analogy. And this viewpoint, this way of seeing things, allows one to understand certain concepts in sister algebraic theory by looking at their analogs in topology. Meaning that if I give you a definition in sister algebras, you can apply that definition to the commutative case and see what happens at the underlying space. And if you get a well-known property in topology, you might think of the sister algebraic definition as a non-commutative version of the topological definition. Okay, loosely. This is just an analogy. And so, well, with this, I can now explain what these words mean, at least in form. Separability, simplicity, being unital, being nuclear, and that's it. Okay. But what I'm going to do, as I just said, I'm going to state definition for sister algebras, and I'm going to look at what happens at the spaces of commutative systems. So first of all, of course, this is trivial. A sister algebra is unital if it has a unit for the product. And if you study unital commutative sister algebras, you realize that these are precisely the ones that have a compact underlying space. So in a sense, you might view, using the same analogy, the study of unital sister algebras as the study of non-commutative compact spaces in some sense. Similarly, one says that the sister algebra is separable if it counts a countable dense subset with respect to the norm that the sister algebra has. By assuming this in the commutative setting, you get that this is the second countability. Okay, so a commutative sister algebra is separable if only if the underlying space is second countable. So these are 2 out of the 5 definitions that I'm going to make today. The third one is simplicity, and one says that a sister algebra is simple if it contains no proper closed two-sided ideals. Now, do note that I'm assuming, or I'm saying that the ideals have to be closed. So in an algebraic setting, so for algebras, for rings, one usually says a ring is simple if it has no proper two-sided ideals, and that's it. But for sister algebras, because we have this additional sort of structure with the norm, we define simplicity by looking at closed ideals. And well, I'm a bit hesitant to go to the next slide, but still, if you study simple commutative sister algebras, you realize that the only one is the one that has a point as the underlying space, because any open subset induces an idea. That's the general idea. So the only commutative simple system algebra is C0 of 1, so the complex numbers. However, this analogy that I was using in these first 2 lines, I don't think that one should use it for this third one. So, because now we'd like to say the study of simple system algebras is the study of non-commutative points. But a point is something trivial in topology, and simple system algebras are far from trivial. There are plenty of examples of highly non-trivial systems. And in fact, the classification theorem is a simple system. Okay. So these analogies shouldn't be used in this. Okay. The fourth definition is nuclearity. And here I'm not really going to define what nuclearity means. I'm just simply going to tell you 2 words in different settings that look like nuclearity for system algebras. And hopefully you know one of those 2 words. And then that's it. Now, this is cheating in some sense, but nuclear for system algebras, the term nuclear comes from the term nuclear from topological vector spaces, which is something that Groth indicated. So if you know what nuclear topological vector spaces are, you can sort of get a feel of what a nuclear system algebra must be. Now, if you don't know what nuclearity means, you might still know what an amenable group is. And nuclearity for system algebras is, in a very precise sense, the same as amenability. So there is a version of amenability for system algebras, and you can prove that it's the same. Now, you might not know any of these 2 words, but you probably have heard of the Bernard-Tarski paradox, which says that if you take a ball, you can divide it into finitely many parts and reorganize those parts in such a way that you get 2 identical balls. So you can double the balls. It's a paradoxical behavior. And often when you work with groups, you don't want your group to satisfy something of this. And the way of ensuring that the group does not have this sort of paradoxical property is by assuming that the group is amenable. That sort of thing. So in the same sense, when you're assuming that the system algebra is unital, when you're assuming that the system algebra is nuclear, what you're saying is that you don't want Bernard-Tarski phenomena in the system algebra. So you want system algebras to be well behaved in some sense. You don't want to be able to produce these sort of decompositions. Okay, so that's nuclearity, and finally stability. Now, to give you an exact definition of this would require many other definitions. So instead, all I'm going to say is that under these 4 assumptions, so our system algebra, unital, separable, simple, and nuclear, that stability might be regarded as a dimensionality notion. So you might regard that stability as something that says that the algebra is finite dimensional in a highly non-trivial sense. So I'm not saying that the system algebra is finite dimensional, it's a vector space, or something like that. It's something far bigger. And in fact, to put this line here, not only do I have to assume this, but I have to go through a very deep theorem, which was proved by these people. So these are the 5 notions that I'm going to use. Right. So having said that, now a natural question is, well, how do we produce system algebras with those properties? Or more generally, how do we build system algebras? And well, as often happens in most areas in mathematics, you don't need to come up with new examples every time. You can take existing examples and apply abstract constructions that will lead to, presumably, new system algebras. And the 3 constructions that I'm going to be using are matrix simplifications, inductive limits, and direct sums, which I'm now going to explain. So matrix simplification just means that if you take a system algebra and some natural number n, then the n times n matrices over A can be given a system algebraic structure, where the norm is something and the involution is just the adjoint. But instead of conjugation, you put the star operation. Okay. So that's matrix simplification. For any system algebra, you already have a countable family of new system algebras, 1 for each size of the matrix. Now, the second construction, and probably the most important one, are inductive limits. For those of you who have not seen this, I will very briefly discuss what these are. So generally, you can consider something called inductive systems, which are just collections of index system algebras and morphisms between them. And then by using the information of such a system, you can build a system algebra that codifies some of the information in here. And this is known as the inductive limit of the inductive system. Okay. In particular, the information that the inductive limit codifies is the asymptotic behavior of atoms. So just to give you an example, if the sister algebras are contained one inside the other, and you take the inclusion map, then the inductive limit is just the closure of the unit of the sister algebras. More generally, if the maps are not inclusion, because you want to take into account the asymptotic behavior of the points, what you do is this. So you take the disjoint union of the sister algebras, and you quotient this out by an equivalence relation, which says that A is equivalent to B if their image at some point in some K is the same. Okay, so for example, you can take A in A1 and B in A2, and then maybe phi 1 of A is not A. That would happen. But perhaps when you move them by composition to AK, the image is the same. So if that happens, you say that these two are the same in the inductive level. This is not a sister algebra, but you can use this to then build a sister algebra, which is known as the inductive level. Okay. Again, I will give examples of all of this in a second. Finally, the last construction that I need is direct sums, which is rather trivial, if you will. You take two sister algebras, and then the direct sum, the algebraic direct sum, has a sister algebraic structure, where everything is component-wise. Okay, involution is component-wise, product, addition, and so on. And this gives you a new system. Now, despite not using them, let me just mention that there are plenty of other constructions. So that the theory of sister algebras is very rich, and you can construct many different sister algebras. So for instance, starting with a group or with a groupoid, you can build a bunch of sister algebras, which are known as the groupoid sister algebras. You can also consider tensor products, and in fact, set stability has something to do with this, but I'm not going to mention it. You can also do cross products, meaning that you have a notion of a group acting on sister algebra, and you can then perform the cross product of that. If I have the time, I can mention a couple of things about this, and many other things. Okay, so how do we use these three constructions? Well, let's, for instance, start with the complex numbers. Then, by starting with this, which we already know is a sister algebra, we have that all these finite matrices are sister algebras. This is a family of sister algebras, and so we can consider inductive systems. So we can then build inductive limits of these sister algebras. Okay? And this is already a huge family by only using one building block. So by only using C, we've created all these different sister algebras. And this is an important family of sister algebras, which is called the family of UHF algebras. So a sister algebra is UHF if it's isomorphic to something of this kind. Similarly, but by, sorry.
It matters how you include M.
No, so, sorry, I never write this, but presumably there are some maps here. So you take a bunch of matrix algebras and some start homomorphisms. They might not be inclusions. They might be something completely different.
Okay.
Yeah.
And it matters how you.
Yes, yes. Depending on the maps, you get something different. Not always. I mean, you might consider different maps and then the inductive limit is the same. But generally, yeah, exactly.
They could be not isomorphic.
Exactly, yes. So these are UHF algebras. And more generally, what you can do is do the same thing as I did before. You start with the scene. You consider finite matrices of the scene. Now consider direct sums over these finite matrices, and then you do inductive limits of these direct sums. So this is a family that contains UHF algebras that is bigger, and it's known as the family of AF algebras. So again, a sister algebra is AF if it's isomorphic to something of this kind. Okay. Now, the reason why I'm introducing these two families is because they were the first ones to ever be classified in the sense that I want to talk about. Mainly, what was noted about the sister algebras is that you can distinguish between two of them by only looking at their projections. So by only looking at those elements that are their own squared and their own involution. So these are the simplest elements that you can think of in a sister algebra. Right? Everything is trivial in some sense. So the product is trivial, the involution is trivial. So of course, they are really hard to work with, but they are the simplest among the elements in a sister algebra. For example, this is a projection in M2. Some product and so on. And well, what do I mean by these projections being able to distinguish this? Well, Grimm showed in the 60s that the UHF algebra is characterized by not just projections, but equivalence classes of its projections. Not in A, but in A, M2 of A, M3 of A, and so on. So you not only look at projections in A, you look at projections in M2, in M3, in M4. All that. You can consider an equivalence relation, which I'm not going to define. And with this, you can tell two UHF algebras apart by only looking at those equivalence classes. And the formal way of saying this is that if you have two UHF algebras, then they are isomorphic, even if their ordered K0 group is isomorphic. Again, I'm not going to say what this is, but essentially, this is an invariant that you build by looking at equivalence classes of projections. That's all there is. And in general, this appears in many fields in mathematics. This is known as K-theory. So, well, Grimm showed this in the 60s, and then Elliott noted in a paper published in 1976 that you can do the same with AF-algebras. So the result is more general. Right? The class of AF-algebras is bigger than the class of UHF algebras, but the same invariant is still enough. You can tell two AF-algebras apart by only looking at their projections. And so this sort of led to the following question posed by Elliott, which is, can we study well-behaved sister algebras using the same techniques? Now, as I said in this talk, well-behaved means separable unital nuclei. For separability and being unital, just to make life slightly easier. Now, when you ask this, you quickly realize that this class is far too big. It contains many sister algebras. And so a first approach is to say, well, we say something of those that are simple. So you look only at those simple sister algebras that are also unital separable. So the question is now is, can we study several simple unital nuclear sister algebras by using similar techniques? And the techniques, as I sort of alluded before, are K-theory cases. Again, I'm not really going to explain what these two things mean, but the main idea behind it is that you look at projections in A, in M2 of A, in M3 of A, and so on. And then you also construct something that's called the suspension of the sister algebra, whatever that is. That's a sister algebra, and you look at the projections there, but the projections in the 2x2 matrices there, the 3x3 matrices there, and so on. So you look at projections in many sister algebras related to A, and you try to distinguish them. That's the question. This is precisely what it means to be classified by the Elliott model. Mainly, this is a conjecture which was posed by Elliott. It says the following. So take a separable simple unital nuclear sister algebras and consider an invariant which encodes the K-theory traces of a sister algebra, whatever that means. The exact formulation of the invariant is this, but for today, this is more than enough. And well, nowadays, this is known as the Elliott model. And the conjecture was that for separable simple unital nuclear sister algebras, this is enough. So an isomorphism at the level of the invariant implies an isomorphism to the whole system. This really is a deep question to ask, because this is mainly telling you that if you take two sister algebras of this kind, you don't need to look, or you don't need to know what those sister algebras are. It's enough to know something about them, which is not the whole information. And still, by only knowing that, you will be able to say if they are isomorphic. So it's a really deep thing. This implication. The other implication is tricky. Because when I say invariant, obviously what I mean is an invariant under isomorphism. So if two sister algebras are isomorphic, the invariant must be as well. The really difficult part here and the deep part is here. So this was posted in the 90s. I think that the first written reference of this is from 1992. And when this was first posted, most people thought that this couldn't be done, even with additional assumptions, because the invariant is too small and the class is too large. That's simply the sort of idea that was behind this. But well, years went by and positive results started to appear. I'm not going to explain what these classes are, but just know that these are all inside this class, right? And so in the 90s, in groundbreaking work, Kirchner and Phillips showed this, whatever that is. Then, just to name a few of the results out of a really long list, classifications were obtained for certain classes of system algebras in this vein. So they were saying that the Elliott conjecture in these cases was true. So I want to give you a quote of one of my favorite books of classification, which is a quote of a quote in some sense, which says the following. So Edefros, for those of you who don't know, is a really good mathematician, writes about Elliott's conjecture. This was regarded as ridiculous by many, including myself. We waited for the counterexamples to appear. We're still waiting. This was in 2001. This is a book published in 2002, but the preface to this book was written in 2001. The book, this is not the title of the book. The book has two titles and it's divided in like two smaller books. The first part of that book is called Classification of Nuclear Simple System Algebras. I highly recommend it if you're interested in this. It's a book written by The reason why I mention this is because I find it extremely funny that 2 years later, Jordan found counterexamples to the Elliott conjecture. Okay. And so there are counterexamples to this conjecture. So Jordan found some counterexamples in 2003 and found other counterexamples in 2001. So what this means explicitly is that you can find pairs of separable, simple, unital nuclear sister algebras that have the same Elliott invariant, so isomorphic, but that are not isomorphic as sister algebras. So the conjecture that the Elliott classification program, as stated before, is false. And so, of course, now the approach was, well, how can we fix it? Can we add some additional assumption so that then the conjecture is true? And of course, you in some sense already know the answer because I've been showing you the theorem. But the answer is that you need to add Z stability. Okay. The issue, if you interpret Z stability as a finite dimensionality notion, is that in those examples, at least one of the two sister algebras was not Z stable. So it was far too big for the invariant to capture. That's sort of the idea behind it. And so, well, as I said, in both of these counterexamples, at least one is not Z stable. So of course, what's the natural thing to do? Well, let's rephrase the conjecture. And let's say now that the conjecture says that for separable simple unital nuclear that stable sister algebras, isomorphism of the invariant must be the same as an isomorphism of the system algebras. And this, after 30 years, turns out to be true. So as a result, by many hands, as I say here, including but not limited to these references, and decades of work, so 3 decades, we now know the following. So separable, simple, unital nuclear is that stable system algebras satisfying the UCT classified the reality. Meaning that the conjecture is true. Modulo something. Modulo this. Modulo satisfying the UCT. Now, I'm not going to explain what the UCT is. It's a very sort of deep assumption in KK theory, stuff like that, which I don't fully understand myself. But I've been told that it's always nice to finish with a question. So the question is a big open problem in the field of system algebras, which is to determine if all separable nuclear system algebras have this property. In particular, if they do, then you can grant this theorem, which is exactly the conjecture finale. Now, I don't know how I'm doing on time. The pizzas are not here, which tells me that I'm doing great. Okay, so I have a couple of minutes. Just maybe a couple of things that I want to mention about this result. The first one is how to use it. So the good thing about this theorem, now that we know it's true, is that it can be used as a black box. So for instance, you can construct a sister algebra in a very strange way and compute its Elliott invariant and check that these things are satisfied. Then it might be the case that that invariant is exactly the same as the Elliott invariant of a really well-known sister algebra. So by virtue of this theorem, you found another way of constructing a well-known sister algebra, for example. Now, The other application that I wanted to mention, because many people here are from dynamical systems, is that it has applications in some sense to dynamical systems. So as I said before, there is a notion of a group acting on system. In particular, what this means is that if you have a group acting on a locally compact Hausdorff space, this group action induces a group action from the same group to the induced commutative system. So a group action on C0X. And so you can consider the cross product of that, and that's a system algebra, which encodes in some sense the group action. Now, there are certain assumptions on that action that ensure that that cross product is going to satisfy these properties. So for those actions, this gives a complete classification of those actions. Because you take those actions, you consider the cross product induced by those actions. You run this theorem, and then the Elliott invariant classifies. So that's sort of state of the art in some sense. And it's something that many people are trying to see which cross products have these properties, so that we can then apply the classification. Okay, and that's all I wanted to say. Thank you very much.